Thanks very much for watching this. My name is Srinath Perra. I work at Head of Research at WSO2. Today we'll talk about the current state of LLM, SLM-based code generation and future directions. Okay, first of all, this is a huge topic. There are a lot of works going on there. So I cannot cover everything. I will cover some of the topics, mention some of them. And I'll not even mention some of the topics. Okay, so the first question is the code generation a solved problem? If you look from far, it looked like almost like that, right? So the HumanEval benchmark, we had like 94, 96, etc. SWE-beanch verified, we are at about 76%. If you are reading all your Twitter, LinkedIn, people talking about building apps in days, minutes, a lot of success stories. We are now matching Olympiad-level problems and some of the problems these LLM solve. We don't even understand them, they're so complicated. So are we done? However, if you look closely, it's not that simple, it's a bit complicated. There was this paper called LiveCode Bench, came out recently. It was looking at contamination. So the idea of contamination is that the LLMs learn about this benchmark and their answers. So it could happen because the people who build the LLMs feed it directly, but it can happen without them doing that either, because there are a lot of articles, there are a lot of papers, etc., talking about this benchmark, and which means the LLM can learn them, can know about them. So in this LiveCode Bench, they looked at the LiveCode Bench. They defined this benchmark, which you can change the time and select the problems for the benchmark. So you can look at the cutoff for different models and select the benchmark. And what they saw was that when you go past the cutoff, the performance of a lot of models fell by significantly. For example, you can see that the GPT-4 performance suddenly dropping how much? Almost 40% when it goes through a cutoff. And you can see this same happen with the blue line, etc. So clearly there is contamination. So LiveCode Bench proposed a solution that solution is to use the LiveCode Bench, which makes sure that we are measuring the model on the problems that were created after model's data cutoff, which is to solve problems, and the winners only got about 5% correct. They won by basically ignoring everything else. So now, compared to 76% SWE-beanch verified, which is pretty hard. So this suggests something wrong, 5% versus 76%. There are papers arguing when we try to put this into the real world use cases and reporting significant performance drops. And there is this well-known phenomena where that LLM sometimes get these problems that are very easy for humans wrong while doing Olympiad-level problems correct. This is called monotonicity, but this is a huge problem because we can't trust them if they're doing that. And then when we look at certain problems and when we guess how good the model is, that doesn't work that well to generalize. Okay. Now, on the other hand, code generation needs a lot of accuracy. So I teach and I tell my students that when they come in, I do as a programmer, distributed system designer, AI designer, it's a serious business. if a doctor make a mistake, one person may be affected, the person he is treating. But if a programmer make a mistake because the code runs again and again, 10,000 people may be affected, and we might not even know, right? So it's a complicated problem. So the years from when we look from outside, it's look as if this code generation problem is solved. But if you look closely, you see the contamination, you see these concerns, and when you look for the bar, that bar is very high. So I think it's not a solved problem. There's a lot more. This code generation problem, the first, the one that got a lot of attention is single function level or competitive, smaller. You get a problem description, you are supposed to solve it. So HumanEval, benchmark, LiveCode Bench. The second problem is to basically bug fixing, somehow repair, improve the code. The third is translate from Java to Go, etc. That's a very interesting problem. Go from legacy program languages to. Then just there are some languages that are very widely used. There are some other languages which has less data. So can we make the models work for low resource language? How do we measure success in code generation? So the best approach that is been widely used is what we call pass at K. Idea is that there are n test cases. These test cases test the problem. Okay. You are given a prompt, each LLM generated solution. We run the test cases and see can you pass all the test cases. Here the K means the code may generate K answers. Pass at 5 means you generate 5 solutions and at least one of them are correct. You say it's correct. Now, when you come to the real world, this is a higher bar because writing these test cases are hard to. But unfortunately, we don't have a better answer. Now there are these answers like code blue score, which is to compare to a right code, correct code, and compare. But I don't believe it's that accurate. It doesn't work well. As somebody who codes, I don't think it works well. But probably one change that we want to do when we do these numbers is to actually let the models abstain from saying I don't know, because it's very important to at least say I don't know. But that is an open problem. That is my personal opinion. One problem. So there are a lot of other ways to measure success, etc., which I have listed there. One interesting thing is this is what this lot of code IDs, etc., are using. And the developer give you a problem, give LLM problem, LLM give answer, developer edits it and use it. How much change did he do before he is using it? Less is better. That's a measure. Which is a very good measure for ideas, but doesn't work that well for the research, etc., because we don't have human typing. These slides talk about different stages where the code generation happens. So the first part actually shows how the LLM is generated. As we know, as most of us, we go through, when we build LLM, we go through this pre-training. That is to where we give it a lot of text and ask it to predict next stop. So that's how the initial understanding is built. Then we do SFT, this fine-tuning. That means you give input, you give the right answer, and the answer should look like this. Then, so part of this, usually it has a lot of human feedback at that SFT. One other thing that start happening later is this idea of using RL-based techniques, CPO, DPO, JRPO, etc., where we use unsupervised signal from the code to improve. For example, you can ask LLM generate code, and see whether it compiles and give that feedback. So that's a GRPO feedback. Or you can ask it to generate code and test and run it and give feedback. Is it good or not? Good news is when the people build foundation models and LLMs, they train their models. They are doing a lot of these because they are much cheaper compared to using human feedback. And it has been shown that doing this actually improve the reasoning skills of the LLMs. So the good news is that a lot of LLMs already have pretty good code generation skills. And also part of this training, they usually have ability to have a code, have an instruction and change it. Or have a code, have an error message and fix it. So a lot of these skills to improve are built into the LLM and they are being built more and more into the LLM. So far, we talk about what comes built into the LLM. When I say LLM, a lot of those apply to the SLM, small language models. So on top of that, so the one part of code, what we can do to improve code generation is we can do this GRPO, DPO, PPO training, that is to continue what the foundation. We can do SFT on using high quality data sets. We can do distillation, learn from a bigger model and teach in a smaller model. So that is a one layer. And then you can go to either for prompt or inference time scale. So we call inference time. This is the idea that after we ask LLM to generate a code, we can do something such as we give feedback or we run and see what happens. We run it again, test cases and give feedback back and ask LLM to improve, right? Or it can be even you get the code and ask LLM again, this is the prompt, this is the answer, is it correct? If not, figure it out. Or simulate, think through. So this idea, this whole idea is called inference or test time scaling. It just means that these are things you do after the prompt came out. Let's now focus on the first type of code generation skill, which is to solve competitive problems or single function level problems. It could be like 2-3 functions. It's like few function level. As I said before, the key benchmarks are HumanEval, and LiveCode Bench is much more preferred because it avoids contamination, as we discussed. So there are a lot of papers. I will walk through them and discuss some of the approaches people has used to solve this problem. First one is people use RS, reinforcement learning. Very high level idea is that you ask the LLM to generate the code and run that code directly or against test cases, get outputs and feed it back to LLM and ask it to improve the code, and you run through that feedback loop. As we discussed before, LLM already can get this feedback and improve. This is already built in their earlier training skills. But here, by doing reinforcement learning, more focus, more. So this has been, there are a lot of papers up to until 2023. So there's PPO coder, there's code RL. Right? This improves the accuracy against the benchmarks. One very interesting other way of doing this is we can use this to do semi-supervised or unsupervised learning. For example, I can take code, I can break the answer by putting some errors and ask LLM to fix it and give feedback what was the right answer. And by doing this, now for this process, you don't need to create new training data. You can start with the existing problem code pairs, but then generate a lot of training data on top of that. You can maybe say it's semi-supervised. The well-known paper based on this is Py3 and base up. If you look at the papers based on RL stops towards 24, and the following papers focus on SLMs, not on smaller models, but not on bigger models. However, RL is still useful for when using the SLMs and with low resource programming language and doing things such as building a model that is very specialized, personalized for a repository organization, etc. So RL still has use cases, but agents to grow. Let's move to agents. The idea of the agent is to identify specialized roles that typically humans do, such as writing code, generating tests, verifying them, etc., and match them into agents, and let the agents work with each other and solve the problem. There's this paper, Agent Coder 2023, very interesting, which kind of which got very good results on HumanEval. Their initial results were on 80s, but then they later do, I think 2024, they did an update that took them to 96. The agent code is still interesting. It's very competitive, it's very simple. If you look at it, several pretty simple prompts. There are other methods that has taken over, but it is still an interesting one. It's a good thing to compare against even with when we do the advanced methods. One big learning at the agent code quality of test is critical, because the agent coder generate code and test and run them and try to fix it. However, you usually get in trouble when the tests are not good. So there are other variations. There's intervenor, there's debit code, the map code, etc. Some of these took over agent coder, but then agent coder release update, which actually come back and beat them. A very interesting new approach. Here, instead of generating code and this approach, say, let us simulate. There are key paper is CodeSim. It's again another key paper you should go and read if you're interested. So the one key paper you go and read, you should read 1 or 2 RL papers. Then you should read Agent Coder, because that is key. And then comes CodeSim. The CodeSim basically says, given a problem, we will generate answer. Now, using public test cases. Idea of public test cases is inside the problem, there are few input-output pairs that are given as samples or public test cases. What CodeSim did was, given a problem, it generated the code. It used the LLM to think through what is happening when in the execution and find bugs and fix it. And interestingly, this did better. This was able to beat both the map coder and agent coder. So when this paper came out, the map coder had beaten agent coder. So it is not here, but CodeSim did 95%. We know that agent coder came and did like 96%. There are on later results, actually CodeSim is better. So, but this is a very different approach. So basically, so you can do very well by looking at the code and thinking through it. So this opened a very interesting topic, which is that the quality of test cases are very, very critical for this problem. So if we can generate better test cases, it will help. So there are a lot of other papers happening which are about creating different test cases. such as built-in property test, differential test, the test cases. So any of these ideas can come and plug into the agent coder or the code sim kind of places, because if you can generate good tests, usually tests are, you can test any breakthrough at the test site can improve the results here. So that's it to keep if you are in this. This is, you can go and even argue that the agent code, etc., are also inference time scaling. Let's not get into that debate. Their main difference is they focus on creating a lot of candidate solutions and pick them. So I'll talk about two papers. There's something called Code D. What it does is it's given a problem, generate multiple solutions, generate a lot of tests, and see how much they agree. And they work on the assumption that it is harder to agree on wrong code than agree on correct code. And that using that assumption, they could show that they can get good results. Then there's this 2025 paper which do this idea, but with a lot more detail. That's again a key paper you should read, in my opinion. They got very good results. Then there's another approach. Now, disclaimer, this is one of our papers. This just published. So the idea is that we create a population, multiple code solutions, and we create a population of tests. And we run them and we give them accuracy probabilities based on their feedback. And we use the evolutionary operators to, we pick solutions and test and evolve them and run another population, like that. And using this, we went beyond code sim. If you look at these tables, you can actually see that although agent code came earlier, the map code came later, the agent code and new update is better. But the code sim is better. And this is done, this as you saw, are based on HumanEval. But the relative importance holds for LiveCode Bench and LiveCode Bench because of the lack of contamination. The reduced contamination, we don't know. And so it is, and they are much harder problems. Then I will look at another approach. This approach haven't beaten the benchmarks yet, but I think is very, very promising. The idea is, when we learn programming, we were told to write preconditions and post conditions and looping variants, etc. Of course, we don't. You may have done it at the university, but we don't do it much when we write code. The idea is that actually LLM can do it. You can ask LLM to generate code that does that. There are programming languages that support formal verifiability, which means that when you generate code, they are usually extension to known languages like Python, C, Go, etc. Or either that, or from the formal description, you can later generate the well-known languages. Idea is that you ask, when you write the code, you put the pre-post conditions and invariants into the code. And the compiler goes and checks. And you get a compilation error unless the code guarantees to keep given those preconditions, it's guaranteed to support the post condition. So this is basically provable code. Right? This is very powerful. So the challenge is, now you get the compilation error and you have to keep fixing until you pass the compilation error, which is not easy. So there are systems people have built trying to give this feedback and find the right solution. So you can do with the known benchmark, and there's another new benchmark called SWE-beanch, which is much harder than the HumanEval. Now, there is a very interesting paper. This came out at 2026, sold in about close to 90% problems. When you say solve, that means it can get it to compile, right? Because unless it is correct, it keep complaining. This is after 8 iterations. I think this is a very interesting direction because this is provable correct code if this works. And then we can have, if we can build libraries, a lot of libraries that has provable behaviors, then we write the code, we bring in these provable things and be able to trust what LLM generate much more. So I think key role in the future. I'm very excited about this topic. Competitive level programming problems. Now let us focus on the second class, which is fixing bugs. So given a repo and given a bug description and optionally test cases, right? The LLM supposed to the patch that fix the problem. There are SWE-beanch and there's SWE-beanch live. There are many different approaches. This problem we can broke into 3 parts. This also explains how it is different from the earlier problem. The hardest part of this problem is the bug localization, knowing which part to edit, which context given to LLM so that it can fix the problem. So this is the hardest part. So also we want to generate test cases so that we can have feedback, etc. So, but this test case generation and the earlier test case generation are not that different. But of course, this has a bug report which take things slightly different. And the third one is you have to actually generate the answer and iteratively go and improve that. But that one has a lot of overlap with the earlier problem. Now, so I said there are multiple benchmarks, but there are almost no papers reporting against SWE Live, probably because it's too hard. But there's SWE Live has a leaderboard, and you can see with the state of the art LLM. So this leaderboard show another interesting thing, which is that there are 3 systems, 3 papers, 3 key papers. You can see 2 of them there, the SWE agent, open hands, and agentless, which is new work. So the lot of new work happening, build on top of this, adding bug localization, etc. into those. So let us look at these 3 because I think that 3 is very interesting. So this is I said there are 3 main approaches. First one is that it came out in 2024. SWE agent-based solutions are in number 1, 3, 4, 6 in SWE-beanch live bench leaderboard. What SWE agent? 2 things. It said we'll use the React loop. So you can read about the React loop. It's a most well-known pattern for building AI apps. It says we can use the React loop with what you call agent-computer interface. This agent-computer interface defines set of operations, such as you can search the files, you can edit the files, you can generate code, you can manage context. There's an API and it uses set of operations. And it says the React loop working through these tools, limited set of well-defined tools. And the paper, if you look at the paper, it shows that actually adding too many tools actually reduced. A lot of work that's done later come and take this SWE agent but change different aspects, bug localization. So now remember this work with React, and it's a single agent. Then came open hands. The open hands compared to the SWE agent is multi-agent. SWE agent is a single React agent, this multi-agent. This thing's more like a co-worker working with the humans. It has browser access, it can run commands, etc. Actually, the SW agent can run commands too. One highlight in OpenHands is that it has this event stream, which basically it's a time-ordered things, what happened, etc., that give you a good context. Now remember, because the OpenHands has this browser access, you had to really careful when you run it, and also interpreting the results, because if it go and browse the internet and look for solutions, that will contaminate, because a lot of benchmarks, the answer is in the internet. The third one was agentless. Basically said having multiple agents hurt. Just have a three-step process, one for localization, one for FAR, and one for verification. And it did pretty well. So these are three high-level approaches. There's a React-based single-agent approach. There's an agentless approach of fixed 3 stages versus multi-agent approach. I don't think there's a clear answer which one is better, as you can see from the SWE live leaderboard, etc. So, but something to remember. So all these 3 approaches can work. Now, when you look across, the key problem to solve to do this fix bugs is find the bugs. So there are many approaches. There are you can do simple search and filtering to look for files, select files that are interesting. You can do it with information retrieval based methods or using embedding. So which basically means first look at repo level, find which files are interesting, then look at the files, found what functions are interesting, and then look in and found out which statements are interesting, then do this and basically give it as context to fixing things. Key papers are autocode drawer, bug separers, agentless, etc. So there are new methods being proposed: depth first search on code dependency graph, causal reasoning, RCA, etc. So I have list. I haven't gone too much detail into this. But if you are working on this, the bug localization is a key problem. I believe it is still an open problem. So I will talk about one more subtopic. We wind up. So low resource languages. These are languages that don't have enough samples. How can we improve the results? So this one, basically RL-based methods are used. There are 2 benchmarks, multiply, which is basically HumanEval convert to other languages. Then AGLCB, this is LiveCode Bench, ported for other languages. So that is all through SFT and JRPO and other RL-based methods. So these results are for Julia. So usually the results come from 40s to 60s. Quickly going through different approaches. First level is that you can generate code. You can try to compile and give compiler feedback. Just this get things to compile, it doesn't necessarily code correct. You can generate code and test and run them, but after some time RL process will learn to cheat, and the RL rewards increases, but your out of the fold results decrease. And then there's this 2026 paper, Agnostics, which is very interesting. It says that a lot of these problems, when you go to competitive programming platforms, now there's a problem. Now, if you're looking for Julia, there's not that many Julia sample code. However, for that, there are a lot of problems where their Python answer is there. So, and verified answer also. So why don't we run the Python code and get the output and use that as ground truth to give feedback, etc. And using this, they got to the 60s on this benchmark. So this is also a very interesting area where work is happening. We basically discussed 3 problems: competitive coding, bug fixing, and low resource languages. But there are a lot of adjacent problems, such as how can I port patches, how can I port dependencies between different versions of the reports, language translation, how to improve the performance, cost, energy efficiency of generated code, security vulnerabilities. How can we generate code that is easy to explain, explainable, easy to explain, understand by the users? Then we can use the human feedback. This is very useful for the real world improvement. Can we build code generation that is specialized for organization or repository, etc.? Can we reduce recreate in the wheel, because we want LLM not to rewrite things that are already there, but don't do too many hoops to just reuse things to get the right level like a good program. So a lot of these, there are a few papers on each of these, but not that much work. So open very interesting areas. And finally, I'll talk about where you can find data. There are benchmarks, but you need data to train, data to work. So computer program platform has a lot of good data because they have problems, multiple verified answers in multiple different languages. As the agnostic paper did, you can use them as ground truth even for other languages. So then the open source code has a lot of things, because if you go to a repo and look through the history, you can see the bugs fixing, you have issues, you have fixes, you know the changes. Now this library was updated, etc. So if you look through the history, there are so many ways to generate interesting sample data, training data that you can use to solve these problems. Now, final takeaways. Correct. This is serious problem. Correctness of general code is critical. Until then, we can't use them for critical things. Hopefully, we won't, because if we do, we're in trouble. Contamination is real, so really pay attention to live benchmarks. Use them as much as possible. Tests are critical. If you have good tests, it will drive the correctness. And basically, test that doesn't handle edge cases actually will hurt, because these approaches, because it passed public test, it will be very positive and stop looking early. Because until I see the results, I didn't so it worked that way. Bug localization is a challenging problem, and there are a lot of unexplored adjacent problems. Thanks very much. Hope this was useful. If you have any questions, please comment. Thank you very much.